Okay, welcome everyone. Greetings from Chicago, where they've been celebrating St. Patrick's Day here and dyed the river green yesterday. It's been very interesting, and now it's snowing. So we have a fabulous meeting today with Dr. Peter Tass, and we're also going to be celebrating our third anniversary. This weekend marks 3 years that we've been meeting together, which is really an amazing feat. And we're going to play a little bit of Mad Libs in throughout the morning. And with that, I'm going to turn this over to Dr. Peter Tass. And unfortunately, I don't know what I did with your bio. So if you can tell us a little bit about yourself. Peter Tass has been working on vibrotactile coordinated gloves, which everybody is interested in getting. And I've seen some advertised on Amazon for Parkinson's. I don't know how those work compared to what you're doing, or vibrating plates. I mean, there's all kinds of vibration things out there. I do know that when we went to Africa on safari and we were in a Jeep, I felt better at the end of the day after riding in a vibrating Jeep all day long. So it definitely helped my tremor. So I think you're onto something here. So if you can enlighten us about these wonderful gloves and how can we all get them or get involved in your study? I think that would be the most important thing. So Dr. Tass is at Stanford. He's been featured on NBC and other shows, and we welcome you.
Thanks very much, Sharon. Can you hear me just for technical reasons?
Yes.
Can you hear me? Okay, perfect.
Yes.
Thank you so much for the invitation. It's a pleasure to participate in your meeting. Just a few words. By training, I'm a medical doctor, I'm a mathematician and physicist. During my medical studies, I got intrigued by what's called self-organization processes, by the fact that so many thousands and thousands of different subsystems, suborgans, organs, and cells beautifully working together, both under healthy conditions, but also under pathological conditions. And this is why after my medical studies, I also studied maths and physics, then also I'm from Germany, also made a habilitations like a PhD, another PhD in physiology, and worked also on the wards in neurology, and had a chair at the University of Cologne in neuromodulation and an institute in one of Europe's largest research centers at Jülich, but couldn't do the clinical research at a speed I would love to do it. And that's why I finally moved to Stanford, and where I really love the working conditions very much. It's a first-rate place for clinical research. Now, our approach aims at the following. We develop stimulation techniques by means of maths and physics, meaning we use self-organization processes and plasticity rules, learning rules, as you'll see, as I'll explain later on, in order not to simply suppress abnormal activity while we're stimulating, but to reshape, to change the brain, to change the connectivity patterns in the brain in a way that the brain unlearns the abnormal connectivity patterns and hence is no longer able to produce abnormal neuronal activity. So that's the very goal. It's very different compared to standard deep brain stimulation. And Parkinson's disease is characterized by abnormal neuronal synchrony. Why is synchrony something really relevant to the nervous system? On the one hand, it's a question of the dose, how much synchrony is present. For example, under physiological conditions for information processing, it's absolutely important that groups of neurons are able to synchronize during short periods of time, and that they process information together, that they wire together. Those neurons that are strongly, or that they're basically doing more or less the same thing over a certain amount of time, they get strongly connected. But it's a question of dose. So if there's too much synchrony, that's detrimental. That's not good for the brain. For example, there are neurons that control, for example, the movement of the index finger movement, neurons that are controlling this finger and the pinky and so on. But if all these neurons are in complete synchrony, we cannot do these different movements separately. That's very important. Imagine, for example, a company where all employees are doing the exact same thing, student work. And the same with the brain. So neurons have to be free in order to do their information processing jobs. And that's a huge issue in Parkinson's disease. As a consequence of the lack of dopamine, the connections get stronger and neurons start firing in synchrony. And as soon as they're firing in synchrony for long periods of time, they get strongly connected, and ultimately they can't do anything but fire in synchrony. Now, what's been developed in France, and then, for example, later on came to Germany, and then even later on to the US, was deep brain stimulation. And what's quite remarkable are the acute effects. If properly placed, the electrodes are properly placed, as you can see, for example, here. So this is a Parkinson patient, 48 years old. He's a right-handed and right-sided Parkinson's patient, and the electrode is placed in the contralateral thalamus, ventral intermediate nucleus of the thalamus. Here's the cable, and this is the important thing. So the stimulator gets turned off, and you see that the symptoms come back tremor within minutes to half an hour, and there's even a rebound phenomenon, meaning the rebound is really particularly strong. It's even stronger than prior to turning on the stimulation. And it was a huge advantage, a huge major breakthrough, but it has limitations. On the one hand, there are no long-lasting effects. And this means that we typically have to stimulate 24/7, and this causes relevant side effects. In the meantime, there's even the term DBS-induced, deep brain stimulation-induced movement disorders. Depending on the target, where the electrode is implanted, there's a typical group of side effects that can occur. And a major disadvantage of deep brain stimulation is that it can make speech and voice even more difficult, and it does not really effectively treat so-called actual symptoms, in particular gait and balance issues. So when deep brain stimulation came from France to Germany, I was intrigued by the effectiveness, but on the other hand, it was really a weird thing, in my view, to treat neurons in a way that you permanently bombard them with a long-term periodic pulse train, because that's not the way how neurons talk. That's not a very natural type of interaction in some sense. And therefore, our approach is to specifically counteract abnormal neuronal desynchronization in a very mild way, namely by only desynchronizing it. You can do all sorts of things with abnormally synchronized neuronal populations. You can suppress them, inhibit them, you can induce artificial rhythms or whatever. Our goal is to do as little as possible and to just desynchronize them. Because the important point is, when they're desynchronized, when the rate of coincidences decreases more and more, their connections get loose and loose. The synapses between the neurons get smaller, weaker, and ultimately the neurons are, so to speak, liberated. They can do their information producing jobs again. And this is something one can study also mathematically and in physical models and computational models in high precision. For example, this is a schematic of a group of neurons, and even the simplest small networks already show this phenomenon. So each ball symbolizes a neuron. These connections symbolize the strength of the synapses between the neurons. What you see here is so-called raster plot. So the x-axis is the time axis, and this is the neuron index, the number of the neuron. And you see they're pretty synchronized. They're all firing at this more or less at the same time. And what we want to do is we want to bring them into this state where these neurons are only weakly physiologically connected, and they're firing in a desynchronized way. And the important point is that already the simplest neurons are what's called in mathematics multi-stable, meaning they're qualitatively different stable states, so-called attractive states. And this is illustrated here. What you see here is just a potential landscape. And this minimum corresponds to an attractive or pathological state. This is this type of abnormally synchronized activity of strongly connected neurons, and a more healthy type of attractor, which corresponds to weakly coupled, physiologically coupled desynchronized neurons. What we want to achieve is we want to move the neurons into the basin of attraction of the healthy state. And this is the important point. So our goal is not primarily what happens during the stimulation, but what is the outcome of the stimulation? Are we able to achieve long-term effects? And we've developed a number of desynchronizing stimulation techniques. Some are beautiful from an academic standpoint, others are not really applicable and whatever. And coordinated reset is a stimulation technique that's very simple, and in particular for clinical applications, quite robust and reliable. And it's shown here. So what you see here is a bunch of neurons. Each gray ball corresponds to a single neuron. And what one do now in terms of, let's first start with the invasive approach, deep brain stimulation, then we go to the vibrotactile stimulation. All this comes from the entire development originated from deep brain stimulation work. What you would do is, for deep brain stimulation, for standard high frequency deep brain stimulation, is you have an electrode implanted, as shown here, and then you look for the most effective contact or contacts, and then you increase the amplitude still below side effect thresholds, but you try to reach everybody in order to, and this is not yet clear whether it's an inhibition, whether it's a blockage, or what you actually do, but in order to stop the neuronal activity. Coordinated reset is very different. What we want to do is we want to stimulate in a very mild way. We stimulate different subpopulations at different times, and they should be separate. We have to stimulate them separately, and therefore we cannot turn up the amplitude, because otherwise we would stimulate with huge overlap. And we simply reset them. We restart the rhythm of these different subpopulations by delivering sequences of stimuli to different contacts. This causes a disruption of the synchrony. Neurons are in a desynchronized state during a particular time, during a certain time. And if they're in this desynchronized state for a sufficiently long time, that's the important point, they unlearn their abnormal connectivity. So it's a slow process. That's not a type of thing where you just turn on something, like if you turn on or off the light, but it's taking place in a longer time scale. And it's a mechanism that's important for all sorts of things, for memory, for information processing. When we, for example, talk to each other, or when I give the presentation now, this mechanism is also active while you're digesting what I say, while you're trying to memorize what I say. And my goal is that the trace that that there's an effect of this presentation. I try to make it as clear as possible so that you can memorize as best as possible. And while you're memorizing, your synaptic connectivity patterns in your brain change. And the same principle is what we use for our treatment. It's an unlearning, it's a training type of thing. And how does it look like, the stimulation? Well, we simply deliver short electrical bursts. There's a periodic backbone. This corresponds to the main period of the dominant of the pathological rhythm, and there's a periodic backbone, and there's some randomness, so we change these sequences. And just one computational slide in order to illustrate the mechanism of action of the stimulation. So this is standard deep brain stimulation. What you see here is the neuronal, the y-axis shows the neuronal activity, percentage of neurons firing per time unit. The x-axis is the time, and we turn on stimulation, we block the neurons, we turn it off, and it comes back immediately, as you've seen in the video. And this is now coordinated reset stimulation, and on purpose with very weak intensities, with very weak amplitudes. So what you see here is the amount of synchrony, the amount of coincident firing, the amount of neurons being active at exactly the same time. So 1 is maximum, 0 is minimum. And if you turn on stimulation, you see that the amount of synchrony decreases, but it's not perfect. It's simply because it's a very weak on purpose for the cellular illustration, very weak type of stimulation. Nevertheless, this hugely important mechanism kicks in. What you see here is the mean synaptic weight. So the average strength of the synapses connecting all the neurons in the neural population, and see how beautifully it decreases more and more. And ultimately, after a while, we can turn off stimulation because it's downregulated. The mean synaptic weight has decreased and is there in a stable way. And the neurons are no longer able to synchronize. So this is the goal. We really want to change the microanatomy, so to speak. We want to change the synaptic connectivity patterns in the brain. And this is just for sake of illustration. These are MPTP monkeys. These are seconds. It's 16-fold velocity. It's a measurement cage where we used a light barrier system in order to objectively record movement production. These are macrocumulata. They don't have tremor in the Parkinsonian states. MPTP is a neurotoxic substance that destroys between more than 90% of the dopamine producing cells. So this monkey only has between 5 and 10 of the dopamine producing cells left. This little head protects the electrode. There's an electrode implanted in the SDN. The subthalamic nucleus is standard deep brain stimulation target. From being pulled out, we stimulated the monkeys only 2 hours a day. It was an external stimulation, so the head was taken apart and we connected it to an external stimulator. Monkeys were completely off medication, and this is the same monkey after only 2 hours of stimulation. And that's important. So the monkey has only 5 to 10% of the dopamine producing cells left, corresponding to very, very, very late stage Parkinson's in humans. And concerning the movement production rate, the monkey behaves like a normal monkey. There's no difference. And the effects, and that's the important point. So we stimulated these monkeys. It was a crossover design. We tested different types, also standard stimulation. We've seen that the effects vanish within 30 minutes and so on. But the important point here is the effects persisted after 5 days of stimulation with 2 hours a day for a month. So monkeys were massively improved, significantly improved for a month. And this was independently reproduced by a number of groups in the meantime. And this is the proof of concept we did in Parkinson patients. So the electrodes were implanted, not yet the cables, not yet the cables and the IPG, and patients were externalized. They were stimulated through a portable external stimulator, and we looked at them during the first 3 days. This is a 49 years old Parkinson patient, and you see the patient also suffered from a dystonia for more than a year. She was a right-handed person. She's now instructed to stretch her fingers because of the dystonia. She's not able to do so. She was not able basically to actually use her right hand. And this is directly before turning on stimulation. This is 4 days after electrode implantation. We've measured, and you see the full-blown symptoms, dystonia, tremor, and we measured EEG, muscular activity. And this is about 20 minutes after turning on coordinated reset. And this is invasive. This is through one-sided SDN electrodes. Sorry, why does this not? So this thing has a hiccup. I don't know why it didn't work. And the important point is, due to technical limitations, we were only able to stimulate patients unilaterally. And you see the full-blown symptoms. And this is important. This is about 20 minutes after turning on CR stimulation. And you see that the symptoms are gone, and remarkably also dystonia, because dystonia does not hardly, regular deep brain stimulation is not really effective when delivered to the SDN, and it also takes a couple of weeks. But this is the main message. So this is now 1 hour after turning off CR stimulation, and you see that the effects persist. That's very, very different from a clinical perspective, very, very different compared to what we know from regular deep brain stimulation. And we also recorded the local field potentials, the rhythmic oscillatory activity from the midbrain in our patients. And this is shown here. This is the exact same patient. So we used the same contacts for recording that we also used for stimulation. What you see here is the x-axis is the frequency axis, the y-axis is the spectral power, tells you to which extent this particular rhythm, 4 Hertz, 5 Hertz, 6 Hertz, and so on, contribute to the signal. And this is before stimulation. You see a huge tremor-related 5 Hertz peak, and then the beta band peak. And this is 1 hour after a 2 times 2 hour session with CR. So these rhythms are gone. And this is totally different compared to what we know from regular deep brain stimulation. After effective regular deep brain stimulation, this peak comes back after 12 seconds. And this one basically comes back immediately as soon as the measurement artifact is gone. So this is important. And we've done this, published this for a group of patients, or same effects, very encouraging. But the important point is it would be highly desirable to provide patients with a non-invasive approach, with a non-invasive variant of deep brain stimulation. Now, why is this? Why did we think that this is important? Apart from, of course, occasional, so to speak, observations, as already shown by Sharon. And the other thing, of course, also is deep brain stimulation. No matter how good you are on, there are centers that are really, really good and really careful with respect to electrode implantation. It will hardly ever be a mass market type of treatment that reaches out to all patients. I mean, we have to be realistic about it. And it comes with risks. It's a surgical intervention. And first of all, we are guided by computational predictions. Now, the important point is in the 1980s, so in the 80s of the last century, there were a couple of really interesting experimental studies that showed that you can reset, in other words, that you can restart the rhythm of periodically active neurons with all sorts of stimuli. You can use electrical stimuli to the soma, to the cables of the neuron, to the dendrites, to the axons, to the synapses, so to speak, the input organs. You can use thermal stimuli, chemical stimuli, optical stimuli. This is a very, very fundamental, very robust mechanism. And what we've shown is also computationally, this is enough for coordinated reset to be performed, because we do not need to increase the firing rate or block the neurons, downregulate the firing rates. What we only have to do is we have to restart the neurons at different sites at different times. And for this type of intervention is sufficient. And there are a number of really fascinating, beautiful studies by Len's group. He's a neurosurgeon. What they did is in humans, in patients during operations, in Parkinson patients with essential tremor, with dystonia, chronic stroke, and pain patients, what they did, they've shown the following. They recorded from the thalamic somatic sensory nucleus. This is the main input nucleus. So, for example, when we have the sensation of touch, and if there's vibration or whatever type of mechanical stimulus, these neurons in this so-called ventral caudal nucleus of the thalamus, they respond. They have to process this information. And what they've shown is that these neurons respond to vibration in a beautiful way, in the way we'd like them, so to speak, to respond. Namely, they cause a phase locking. Phase locking means the following. So this is the vibration signal. This is the vibration of our skin. And these neurons do not respond sometimes here and sometimes there or whatever, but they have a preferred phase relationship. For example, always at this mountain, so to speak, of the wave, they always respond close to this mountain. And that's what you see here. So what you see here, the x-axis is a cycle of the vibration. The y-axis shows you a large, what you collect, the data you collect after a larger number of vibration cycles. And you see that this neuron has a preferred phase relationship. Without this phase locking, it would be a homogeneous, it would be a flat line. But this neuron, and of course it's noisy because it's a biological system, but this neuron prefers this phase to discharge. And that's what we need. So we need to be able to control the discharge, the timing discharges of the neurons. And now why gloves and why fingertips? Because the fingertips have on the one hand, they represent a very small portion of the entire skin surface, but they represent a huge amount, relatively huge amount of brain tissue. And that's what's called homunculus. So the sensory map, same holds for the motor cortex. The sensory map has a huge representation for the hand, for the fingers, and for the fingertips. That's the important point. And what we want to do, and that's what we know from computational studies, preclinical studies, and other clinical studies, is that the effects of desynchronizing stimulation, of coordinated reset stimulation, they propagate. So they do not stay at a particular target brain area, but they propagate from one hub in the brain to another. And in order to be effective, in order to build up this propagation as quickly as possible, we use this entry point, so to speak, into the brain that has a relatively large brain volume from where on these effects may propagate. And accordingly, we developed this. It's the first prototype. It's a clunky thing, but it did its job. We're currently developing a next generation glove system, beautiful, with very capable people in industrial design and wearables and electronics. And what you see here is these are mechanical stimulators, and this is now the stimulation pattern. And if you compare it with what we did for coordinated reset deep brain stimulation, the only main difference is that we replaced electrical bursts delivered through contacts of the depth electrodes by vibratory bursts delivered through the fingertips. That's all. And the good thing, you see, if you implant an electrode, let's assume this is the target area, and here's an electrode. You never, or not always, have a perfect, for example, central type of implantation, because anatomy doesn't care about where you would like to implant your electrode. Sometimes you're a bit here, sometimes you're a bit there. And depending where your electrode is, you may stimulate neighboring areas. This causes side effects. And the other thing is, these targets are not homogeneous. So in other words, there are cells, but there are also fibers passing through. You'd like to avoid the fibers, but you can't. And this causes side effects. And that's a dilemma for deep brain stimulation. That was also a reason why from the very beginning we designed very mild, but nevertheless effective as a goal, deep brain stimulation techniques. The good thing here about the glove is we know where we stimulate, the anatomy is intact and reaches the target areas in the brain and stimulates only the neurons we want to stimulate. It does not stimulate the fibers that go through these brain areas. You see, that's very important. And therefore, although we are more distant, we're more remote with respect to where we stimulate, it might really play out ultimately that we take a more distant type of approach. Now, I'll show you a couple of slides and then for illustration, a couple of patient videos and explain how the stimulation works. So these are data from a pilot study. In that study, we wanted to enroll 20 patients and treat them for a very long time, for more than a year. But then COVID hit us and we had to stop the study after only 3 months, after only 6 patients had their 3-month in-person visit. And what you see here is, and in the first few slides are about so-called off medication, MDS-UPDRS Part 3 motor scores. Off medication means these patients were evaluated after really thorough medication withdrawal. Depending on the half-life of the medication, they had a medication withdrawal between 12 up to 48 hours. So they came in not really in their best shape, of course, because but this is important in order to understand the effect of the stimulation and without any interference of medication. That's important. So this refers to the following. Patients came in at 8 a.m. in the morning. We did this motor score, and then they stayed off medication, which is normally quite challenging, of course, for patients. They stayed off medication for 2 times 2 hours. So it was 2 in the morning, lunch break, 2 in the afternoon. And then at 3:30 p.m., we did another motor score. And you see patients didn't get worse, although they didn't get any medication, but they improved significantly. I'll come back to the single patients afterwards. And this was then the long-term study. So the same patients on the first day of the long-term study, again at 8 o'clock in the morning, off medication. And this is after 3 months off medication. And that's important because patients improved significantly. You see, without medication, the influence just caused by the stimulation. Now let's look at the different at the single patients, because that's important, because we want to know whether how these patients actually reacted to the stimulation and whether the stimulus effects were clinically significant or only statistically significant. For example, you can use a large population or can perform a trial in a large population of patients and you might have a statistically significant effect, but clinically it's not significant because it's tiny, but nevertheless, since it's a huge group, you can claim statistical significance, but that's not what we are interested in. And there's the concept of the so-called MCID, minimally clinically identifiable difference, meaning if patients have an improvement, if their scores decrease by more than 3.25, they're improved in a clinically significant way. They really feel, I'm feeling better. That's the important point. The MCID tells you whether it's just a tiny bit of improvement or whether somebody a patient, a subject would really say, well, okay, I really feel better. And these are the 6 patients, and that's the acute effect, what I've shown you here. So all of the patients, except for the 3rd patient, all had an acute, nice and acute effect. But nevertheless, patient 3 did not, at least not worsen, although being off medications. And then the long-lasting effect, this was this graph. Concerning long-lasting effects, all patients had a clinically significant effect. That's important. So they really improved over time. Another thing is, for example, patients also had an improvement or a drastic change of their medication. So on average, they had to take less medication. In some of the patients, this was a dramatic improvement because of the side effects that were gone. And there's one finding we were really surprised of because we didn't expect it, this huge improvement or huge change. You can record what's been done in many studies so far, as you recorded, for example, from the depth electrode, from the basal ganglia, from the thalamus, and there you can nicely see this abnormal Parkinson's and tremor-related activity. I've shown you one slide before. However, it's not so easy to find clear signatures of Parkinson's from EEG signals, from cortical signals. So what you see here is, what we did is, in this 3-month trial, We recorded also off medication. That's important. Also after medication withdrawal, we recorded spontaneous activity. Patients are just sitting in the EEG chamber. We recorded them, and we focused on this primary motor and primary sensory cortex, on the so-called sensory motor cortex, simply because it was only 6 patients. And and this is before glove treatment, and this is after 3 months, 4 hours a day, in total 4 hours a day glove treatment. And the only frequency band where there was a significant change, but very pronounced change, was the high beta band, the typical Parkinson's related frequency band. And you see there's a huge amount of synchrony before the treatment and a significant, highly significant decrease after 3 months. So really, here you see the color coding. So red means very, very strong synchrony. Blue means there's no synchrony anymore. And you see how nicely it decreased. That's very important. Didn't expect it to be so pronounced. That's super encouraging. And we did a couple of case series. We followed up patients for a long period of time in order to understand the stimulus responses, in order to be guided for study design, future study designs, and so on. And again, we measured the end motor scores off medication, after medication withdrawal. It's very important. Again, off medication. And what you see here, the x-axis is the days of vibrotactile stimulation. So 2 to 4 hours a day. And this is something like 9 months. This is half a year. And we had 3 patients that we were able to follow up from the pilot study for a longer period of time. And this is one of the patients who fortunately also was able to receive, and these were our motor scores, done at Stanford, and then the patient had an excellent movement disorders specialist who did all the other motor scores. So these are 6 months, 2 to 4 hours a day, a 1 month pre-planned pause, patient didn't get worse, and then another 6 months with a maintenance dose, only 1 to 3 times 2 hours a week. So not much. So after a while, that's our experience, patients do not need much of the stimulation. And you see in all of these graphs, so each dot corresponds to a visit day where the patients are off medication. This patient were able to tolerate being off medication for 2-3 days. This one only for 1 day, and here study protocol was that it was only 1 day. And you see in all of these patients, the motor score decreases statistically in a linear way. And that's important because the patients really get better. There's something really changing in the brains of the patients, and that's really hugely important. And I show you now a couple of videos to illustrate how the treatment works. So this is a patient who was diagnosed in 2007. He took a huge amount of medication, 20 to 25 carbidopa, levodopa, 25/100. It was about 50% of his time. It was in off time, basically lying in bed because he wasn't able to move. He used a cane and was supposed to use a wheelchair because he was falling more and more often. And he's here instructed to simply enter the room. And unfortunately, you're familiar with these issues, of course. The shuffling, patient has no or hardly any facial expressions. The arms are not swinging. This was in July 2018, and then came to us in August 2018, and for a 3-day visit. And I told him to take as much medication as required in order to feel well. So there was no instruction to reduce medication, but most of the medication he took was short acting, and hence he sort of titrated the medication he needed. And from day one on, he went down to about six to seven was his dosage then for quite a while. And this is the patient now after 2 times 2 hours glove treatment in the evening. And you see this remarkable change, the nice gait, swinging arms, facial expressions. And then after 3 days, he went home again. And this is the 6th day of stimulation at home. At the beginning, only 2 hours per day. And he was able to do work again. And the amazing thing is, and that was very surprising to us, to be perfectly honest, that's why we didn't measure it in this study, because we didn't expect it. Not only this patient, but all our patients with a pronounced olfactory impairment noticed an improvement of the sense of smell and taste. For example, with one patient who was who got the Pennsylvania smell test administered on a regular basis in his Parkinson's clinic, and he was in the pilot study, and after 3 months of glove treatment, he was able to detect all odors, all test odors, and prior to the glove treatment, he was only able to detect one, the wood fire. This is quite striking, quite surprising, and we'll start new studies in June, July. As soon as our next generation glove system is ready, it will enable personalized treatment, really adapted to sensory characteristics, skin thickness, and all this. And one study will be in early stage patients. There will be a couple of studies also in late stage patients, but one study will be in early stage patients where we'll study the impact on olfaction, but also on vision, because for example, we had one patient who came in the second day, was hugely improved with respect to gait and balance. And then he said one of the most striking things for him is that everything's so bright and the colors are so strong. And that's a phenomenon that's known from DOPA treatment, from the honeymoon phase when you start DOPA treatment. And so obviously the glove might also impact sense of the vision, because it's known that, for example, if this is the time axis and if you deliver a simple checkerboard type of flash type of visual evoked response experiment or test, then it takes some time for the visual cortex, see in the occipital part, to respond to this flashlight, so to speak, to this checkerboard pattern. And this latency between administering the visual stimulus and the reaction of the olfactory, of the visual cortex, this latency is increased in Parkinson's patients, and the increase correlates nicely with symptoms, with overall symptoms. And we want to study not only the motor system, but also non-motor symptoms, including vision and olfaction. And finally, he was able to run a marathon and this also triathlon last year. So this is from the so this was from last year's triathlon. He's now with a glove. He stimulates only 1 to 3 times per week, 2 hours, but he's really doing well. So we have a couple of patients that we're following up now for more than 4 years, and the long-term results are really encouraging. This is another patient. He's was a young onset patient diagnosed at the age of 27. In this video, he's about 46, 45. This is the first day off medication. He did lots of workout, but then workout became more and more complicated because of the increasing amount of tremor and balance issues, in particular as you can see on the right side, the right arm is not swinging. And and he was scheduled for DBS implantation. He came to us in July 2018. He was scheduled for 2019 was scheduled for DBS implantation in 2019, and this is now his situation after 6 weeks with a glove. And so far, and since then, he didn't need a DBS implantation. And there's another patient with very pronounced shuffling. So this was the main symptom, the most pressing and bothersome symptom for this patient. That's the first visit on the first day, again off medication. And you see, when you're unfortunately familiar with this, shuffling kicks in when you want to enter or exit a room, when you have to change walking speed, when you have to change directions, and how we, for example, here, you see, it's difficult. And how we provoke it is, we ask patients, how neurologists provoke it is, they ask patients to turn around, as you see here now, in a small hallway. And for this patient, sometimes it was really very difficult to move in a smooth way. It was more jogging type of behavior, also when he was on medication. And this is now the situation after 3 months, again off medication. And that's why the patient reported that with medications he was hardly shuffling anymore. But this is to illustrate why we do this off medication exams. We really want to see the effect of the patient when there's no medication involved. And patient already improved off medication, but you see he's not perfect. Right arm is not yet swinging. And turning around, yes, still has some shuffling. It's massively improved, but nevertheless. And this is also to illustrate that the effects might be huge and even kick in quickly, but when you measure it off medication, it takes some time to ramp up. You see, so typically the amount of medication patients have to take decreases over time, and the effect of the glove increases over time. But one has to spend, so to speak, a couple of months. So for example, this is after 5 months. And this is after 6 months and a 1 month pre-planned pause. He was one of the 3 patients who were able to follow up, unfortunately not with scores, but simply by videos and phone calls. And currently we are developing next generation. Based on further computational research, we are developing next generation glove system, way better one where we can actually calibrate the stimulation, the stimulus patterns to the individual patient. Will be less clunky, modern type of technology, so to speak. And we'll start new studies in about June, July, depending on timelines, whether our contract developers are able to keep the timelines. I hope so. And we'll have studies in late stage patients, in early stage patients, in a variety of different patients. And we had issues because one of our team members had to quit job, unfortunately in the winter break, and we set up everything we wanted to do this year already, and this caused some delay. And finally, we'll soon be able to respond to our vibrotactile CR Parkinson's email in an appropriate way, because we can't just talk to patients through email. There has to be an IRB cleared, HIPAA compliant, so protected health information clear type of interaction. And what we are going to do is we'll send out, currently I only have one brave lab member who's taking care of this. We'll hire more, but we had to wait until funds come in. And we'll send out these electronic screening questionnaires. And in order to really understand whether when a patient approaches us, whether the patient might qualify for one of these studies. So in case you contact us through this email, and I've sent this email to Sharon, then please be patient. It's not that we are not interested in responding to you or helping you. It's just a question of manpower currently, but it'll get better. We'll get there. So thank you so much for your attention. There was one. No, please go ahead, Sharon. Just wanted to respond to some of these questions.
Thank you, Dr. Tass. That was amazing. And I know everybody is interested in taking part in your studies if possible. So let's go to the next couple slides, just a few announcements. The peer-to-peer mentoring program is still going. If you're interested, there's the information. You can check it out on our website. Next slide. And if you're going to the World Parkinson's Congress and you haven't told us, let me know, because we have activities going on for our group. And next slide. Okay, so in 2 weeks, we have urban polling returning. You don't need polls to join us. You will learn about the walking with polls. It's great. April 16th, we have Kenneth Thurman talking about aware and care kits from the Parkinson's Foundation. On April 23rd, Donna Gow will be talking about the latest in DBS from Medtronic. So that kind of dovetails with today's lecture. Next. And this answers your question, Kim. We're going to be reading The Ribbon of Road Ahead by Carol Clubney, who will be joining us at our first meeting on April 16th. And I will put the information in the newsletter tomorrow, but including the link to buy the book. And I think that's it. Oh, and open mic is still going on well. Today we had a wonderful Twitch That Partners meeting. We had 9 women there. It was wonderful. And I think that's it on my end. So let's go to the Q&A.
Should I just answer one question after the other?
Yeah.
Okay. One is, David asked, explain noisy vibrotactile stimulation, please. Noisy means that the temporal, there's a temporal jitter. So there's not this strict periodic backbone, and there's some jitter. And so far, the regular and the noisy vibrotactile stimulation had basically the same results. We are testing a couple of different versions of coordinated reset, not only computationally, but also in our experiments, in our studies. And then Barbara asked, do researchers know why the neurons become synchronized to begin with? That's a very good question. To some extent, yes. To some extent, well, basically, it's because of the lack of dopamine. There's a huge body, preclinical body, meaning animal experiments. There are many studies in humans. For example, what you do is, or what people also do is they use the abnormal rhythm, the abnormal synchronization in order to guide implantation, or to be guided to use the proper electrodes for deep brain stimulation. So there's quite something known, but still not everything. But synchronization is hugely important in Parkinson's, even if we don't understand all aspects of it. Can I trial glove in UK? Mary asked this. There might be a trial in Europe, not in the UK. I don't know, but this is something we are planning, and as soon as we know this, we'll advertise this or we'll announce this on our website. But this is something that will take a bit more time, a few more months. And then there was a question: Did we work with patients who have DBS, STX, and can it be changed to CR? Yeah, this is we are planning a trial in chronically implanted patients, but this is still on a trial basis, and since we need, let's say, the invasive type of treatment is from a regulatory and logistic standpoint way slower than the non-risky or type of vibrotactile stimulation. We will hopefully do this year, and again we'll announce it on our website as soon as we start. Why does it take so long to get FDA approval? That's a good question. I mean, no matter, even if you have a non-risky device, you need to get through certain procedures. We were not very lucky in the past with our industry collaboration, but are now confident that we found the right partners, highly professional and also financially very strong partners, so that we will get this as soon as possible. But nevertheless, it'll take 1.5 to 2 years. That's the way it is. Does the glove system help with severe dyskinesia? Yeah, that's our experience. Dyskinesia, actually, levodopa-induced dyskinesia. Dyskinesia is the only symptom. So, well, first of all, the glove, all symptoms, all motor symptoms respond to the glove. Tremor, but also the akinesia, rigidity. But dyskinesia is the only symptom where it's important to adapt stimulation to medication and vice versa. So in other words, if a patient, for example, responds to dopa with dyskinesia, it doesn't make sense to start with, for example, in total 4 hours a day with the glove, because then the dyskinesia goes up. So there are two because the glove seems to replace dopamine on a long-term basis, and therefore there are two ways how to do this. Either one can reduce the medication and then start with the glove, even 4 hours a day, or you start with the gloves only 2 hours a day and then ramp it up. But typically, patients have to reduce their medication. And all our patients so far, but we don't have hundreds. This is something, we didn't treat hundreds of patients so far. Therefore, we still have to be careful. We don't want to overpromise or so. But all our patients with severe dyskinesias had a massive reduction of dyskinesia, so weren't able to perceive them anymore. But it takes time. But it takes, one also has to be mindful with the medication. In other words, one has to reduce medication over time, which of course is a positive thing. Are there trials being conducted outside of Stanford? Not yet, but we are just in the planning couple of trials, as I said, even in Europe. Where do we write to get engaged in the study? That's the Parkinson's VCR email address. Sharon has the email address. And then, as I said, we'll respond to you with this electronic IRB cleared questionnaire. And then just be patient a bit, although we know that we are not as responsive, seemingly as responsive as we'd like to be. Any adverse effects to the gloves so far? No, fortunately not. Will this Any estimate when application for FDA approval will be submitted? Well, I think when the probably end of the year, early next year. General availability of gloves for use by patients. Well, the new industry partners, their goal is to really provide these gloves to everybody, meaning to come up with a business model or provide a business model that's reimbursement based, so that everybody gets it. To the vibrating gloves you can buy now work. I think you mean, Sydney, these are Amazon gloves. Well, first of all, I don't know. The important point is on the one hand, what kind of mechanoreceptors you stimulate. The way we designed our gloves means that we specifically stimulate one type of mechanoreceptors. And then the very important point is, of course, the stimulation patterns. That's what I also wanted to explain in my presentation. So it's not sufficient to just deliver whatever type of vibrations. In order to induce these long-lasting effects, we have to have these specific vibration patterns. I don't know how these couple of gloves on Amazon work, to be perfectly honest. Therefore, I cannot recommend any of them. Maybe you have the link to the website to follow this research. Sharon, I think you have the link to my website.
Yeah, I will put everything out. I will put everything out tomorrow in the newsletter. I'll get you, put the website and the email, everything that you need. Okay.
Can you project approximate cost of gloves? Not yet. It's a question by Susan. Not yet. But as I said, the goal is to make it affordable, not to make a few people rich. Do the gloves have any effect on non-motor symptoms of PD? Yeah, on the one hand, and that's what was quite surprising, as I said, of sense of smell and taste improved, vision improved, but this was not sufficiently examined simply because it was surprising to us. We didn't expect it. Also concerning the typical MDS questionnaires, also constipation improved. And this is a project we'll also do now. We, together with Todd Coleman here, you can measure the gastric oscillations. So if this is the stomach, and then in order to have proper propulsions, there are oscillators in that, so to speak, cause this physiological action, gastric dynamics. And it's known that, and there's a strong connection between these gastric oscillations and brain oscillation, and there's an impairment in Parkinson's disease. And we'll study how this changes as a consequence of the glove treatment.
Okay.
Do other vibrating machines like the power plate on which you can stand have the potential to reduce symptoms? Might well be. I think so. I mean, there are studies about this, but they haven't shown these dramatic long-term effects. You see, our point is, our first and foremost goal is not to induce acute effects, but to induce long-term effects. The acute effects are certainly important in order to motivate patients to use the device, to use the treatment, because if you apply something and you don't see any effect, I mean, you lose motivation. Therefore, acute effects are important, but most important for us is for the design of the stimulation patterns or the long-lasting effects.
I think that's pretty much it. Will you be in Barcelona with us?
No,
yes?
We will not be in Barcelona.
Okay. All right. I am going to get off in a second, but I'm going to have Ashlyn stay on if anybody has more questions. I will get from Peter all the information that you're asking for as far as the website and the email. And thank you for all. I know there are a lot of new people who have joined us today. I will keep you on my email list. And for the guys who joined us, you're welcome to join us some of the time, but not all of the time. I'm sorry. This is basically a seminar, a webinar for women with Parkinson's, but we'd love to see you guys once in a while. And this subject was definitely open for everybody. And with that, I'm going to wish everyone a happy St. Patrick's Day from Chicago. And I will see you in 2 weeks. And you can stay on and ask more questions or talk amongst yourselves. It's up to you. Thank you. And thank you for 3 amazing years, everybody.